Hey guys, my name is David Zhang, and I'm about to do a physics extra credit 3P.36, and this is part A. So the problem is, in June 1997, the NEAR spacecraft, on its way to photograph the asteroid Eris, passed within 12,000 kilometers of asteroid Matilda at a speed of 10 kilometers per second relative to the asteroid. From photos transmitted by the 805 kilogram spacecraft, Matilda's size was known to be about 70 by 50 by 50 kilometers. Their asteroid is presumably made of rock. Rocks on Earth have a density of about 3,000 kilograms per meters cubed. So initially they give you this diagram of where a spacecraft is heading towards the asteroid. And it is 12,000 kilometers distance away in the y direction. And in part A, it says, make a rough diagram to show qualitatively the effect on the spacecraft of this encounter with Matilda. Explain your reasoning. So, as the spacecraft heads toward the asteroid, it is going to go around it in a loop due to the gravitational force of the spacecraft, or of the asteroid. And that's part A. Part B. It says, make a very rough estimate of the change in momentum of the spacecraft that would result from encountering Matilda. Explain how you made your estimate. So we have the fundamental principle of the change in momentum is equal to the net force times the change in time. We know that density equals mass divided by volume. And we need to calculate the mass in order to calculate the force of gravity. So mass equals density times volume. The force of gravity is equal to negative g m1 m2 divided by r squared times r hat. The mass of the asteroid is equal to 3,000 times 70 E3 times 50 E3 times 50 E3. 3,000 is the density, and they give you that Matilda's size was 70 kilometers by 50 by 50. And this equates to 5.25 E17. So the force of gravity is equal to negative g, which is 6.7 E negative 11, times the mass of the spacecraft, 805 kilograms, times the mass of the asteroid, which is 5.25 E17. All divided by r squared. Now they give you the distance as 12,000 kilometers away in the y direction. So it's 12,000 E3, because you have to change it to meters, squared. And that equates to negative 0.01966 newtons. So the change in momentum is equal to the net force times the change in time, which is equal to negative 0.01966 times. The change in time is not given in part B. However, in part C and part D, it tells you that it's a day. So we have to change 1 day into however many seconds a day is, which is 24 hours in a day and 60 minutes in an hour and 60 seconds in a minute. And that gives you that the change in momentum is negative 1,698.95 kilograms meters per second. So now on to part C. Part C says, using a result from part B, Make a rough estimate of how far off course the spacecraft would be one day after the encounter. So we know that the change in momentum is equal to the final momentum minus the initial momentum. We calculated the initial or the change in momentum in part B, and we can calculate the initial momentum from what's given in the problem. So all that's left to find is the final momentum. So final momentum is equal to the change in momentum plus the initial momentum. The change in momentum is found right here in part B, and the initial momentum is equal to the mass of the spacecraft times the initial velocity, which is 10 kilometers per second, which you have to then multiply by 1,000 to change it to meters. And that equates to 8.05 E6. So the final momentum is equal to 804,8301.047 kilograms meters per second. So in part C, we're trying to figure out how far off course the spacecraft would be. So we have to do the position update. And to do the position update, we have to find the final velocity. The final velocity is equal to the final momentum divided by the mass of the spacecraft, which I calculated it to be 9,997.8895 meters per second. So we are given in the problem how far away Matilda is from the spacecraft in the y component only. And in the y component, it says it's 12,000 kilometers. So our equation to update position is R final equals R initial plus V final times the change in time. However, due to the force of gravity, which is negative, we're going to change it to negative VF times the change in time. So what we have is 12,000 meters minus V final, or the change in velocity, which is 2.1105 times the change in time, which is 86,400 seconds. And that equates out to negative 17,347.2 meters, which is roughly 170 kilometers off course. So to show you a rough sketch of what is happening, this is the spacecraft. Initially, it's going at 10 kilometers per second. This is Matilda. This is the initial distance away. And we're assuming it goes around in orbit around Matilda. That right there is what we calculated. So now on to part D. Part D says, from actual observations of the location of the spacecraft one day after encountering Matilda, scientists concluded that Matilda is a loose arrangement of rocks with lots of empty space inside. What was it about the observations that must have led them to this conclusion? So, at first we concluded that Matilda was a tightly dense cube. However, after more observations, we are going to conclude that it is a loose arrangement of rocks, which kind of looks like this. So, the difference between the two is the density. This is more dense, and this is less dense. However, they have the same volume. And we know that density is equal to mass times volume. So, if this is less dense, in order to keep the same volume, the mass has to be less in the less dense form of Matilda. So if we have a lower mass, we have a lower gravitational force. So a lower gravitational force means that there's a smaller change, a difference off course, because we use the momentum principle, which is equal to the change in momentum is equal to the net force times the change in time. If the change in momentum is smaller due to the gravitational force being smaller, then the change off course is smaller because the change in velocity final decreases. So the position update, RF equals RI plus V final times the change in time. If this value right here is smaller, then the change in position becomes smaller. So your final answer in part C will be smaller than 170 kilometers. Thanks, guys.